Good morning, all. Can you hear me? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Thank you, Abhishek. So, in the last class, just I've started discussing limit and continuity. So, I have discussed how to check whether the limit exists for a function of complex variable or not. And I have also shared the class notes, the class material in the respective Google Classroom. So, I think you must have checked this. So, those who have not checked this in the Google Classroom, you may check it later. So, I've in the last class just I have discussed how to check whether limit exists for a function of complex variable or not, and then I have discussed the differentiability of the continuity of a complex valued function, and I have solved one problem also. And the e-material or the study material which I have shared, that is which is a class note. There are some problems for you to solve actually, so you will try to solve those problems. And if you face any kind of problem in solving those problems, you can ask me during the class. Then I can solve those problems. Whenever in solving which problem we are facing some difficulties. So tomorrow also in fourth period I'll be taking one class because Krishna sir is absent in this week. So tomorrow I'll be taking one extra class. So today I'll start discussing differentiability. So before discussing differentiability, just I want to discuss what is the significance of differentiability, and of course, like continuity and limit, the method that I have followed. Here also I'll be following the same thing. That means I'll be discussing it for function of one real variable and function of two real variable. Then I'll incorporate those ideas here to actually identify the methodology or the significance for differentiation of function of complex variable. Okay. Okay. So just let me share my screen first. Just I want to share the blank screen. So can you see the blank screen? Is it visible?
Yes, sir.
Yes, sir.
Okay. So first we'll be discussing the differentiability. So before discussing differentiability, what do you mean by the differentiability? If a function is given y equals to fx, then what is the significance of differentiability or derivative of a function of one real variable? Just I am discussing this for the function of one real variable, which you have studied in class 11. So from the very basics, I'll be starting. So just tell me what is the significance of the differentiation of function of one real variable y equals to fx? Anyone amongst you? Why do we differentiate and what is the significance? Anyone?
So function should not be continuous at that particular point and should be actually continuous. The differentiability signifies simply the function should be continuous and there should not be any sharp corner at that point.
Yeah, the function should be the differentiable function. If a function is differentiable at a particular point, then obviously it will be continuous. Yeah, that is not a big issue.
I'm saying there should not be any sharp corner.
But what is the significance? Why do we differentiate? What are the importance?
The slope.
To get the slope of that function.
Yeah, and again.
Sir,
And another?
if the function is differentiable, then slope exists at that point. Otherwise, the slope doesn't exist.
So what is the significance of getting slope? By finding slope, what we'll do?
So for analysis of curve.
Sir, for calculating the instantaneous rate of change.
Yeah, rate of change is one application. Yeah, very good. And any other?
For drawing graph, I think.
For drawing graph, we don't need the differentiability of a function. Yes, Susmita has told that to get the slope at a particular point on the graph. Yeah, that is right. Okay, so if a graph, the first and foremost thing is that we can get the slope. Slope means if a curve is given, so this is y equals to fx curve. So at any particular point, we can draw the tangent, and the tangent makes some angle with the positive x-axis. So tan of this theta, that is called a slope. So that is denoted as f dash x or dy dx. So main significance is that whenever, what is the significance of differentiation? All of you have studied. We know what is the first principle. That means definition of differentiability. What we are doing here. So let's say this is a point x0 where we need to draw the tangent. So we'll be taking a nearer point which is very close to x0. So that is denoted as say x0 plus delta x. And it's very infinite change we are considering with respect to x0. So this length is delta x. Now we are joining this chord. So since these 2 points on the chord is over the curve, over the function y equals to fx. So the coordinate of this point will be x0, f of x0, and coordinate of this point will be x0 plus del x, f of x0 plus del x. This one. So if I extend this chord, so it will make some angle with x-axis, that is a theta. So if I join this, so this angle will also be theta. Now tan of this theta is actually nothing but this height divided by this base. So height is this length is fx0 del x, and this length is fx0, because this is the ordinate corresponding to this point. So this is fx0, this distance, and this distance is f of x0 plus del x. So ultimately f of x difference will be x0 plus del x minus f of x0, and the length of the base will be this is say x0 plus del x, and this is x0. So this length will be del x. So whenever this point and this point will coincide, that means this is gradually tend to this point along this curve, then this curve will then this chord, the length of this chord will be 0, and that they will be coinciding with each other at this given point. Then this chord will be actually the tangent at this given point. So whenever this point coincides with this point gradually over the curve, then the length dx will gradually tend to 0, because more it will coming towards this point, more it will be coming closer to x0. So that means limit del x tends to 0. So if this limiting value exists, a limiting value of this quotient exists, then we say that the slope will exist, and this is denoted as f dash x. So what are we doing? One application is that we are measuring the rate of change of the dependent variable with respect to the change in independent variable. So here dependent variable is fx and independent variable is x. So the change in dependent variable is actually f of x0 plus del x minus f of x0. And change in independent variable is actually del x. So what Asatto has told is rightly pointed out that we can measure the rate of change of dependent variable with respect to independent variable. Why we are doing so? Because whenever a system is given, so in the system there can be lots of variable. So one variable will be getting there some independent variable, some dependent variable. That means depending on the independent variable, actually the overall properties or the entire properties of the system will be changed. So the property of the system which we are considering is actually the dependent variable. So if we want to measure, say for example, the population of our country. So population of our country depends on many things. Say birth rate, as well as the environment. Everything depends to increase the number of population in India. So we want to measure which independent variable is providing us most significant amount of change in population. So that means we want to measure the rate of change of the population with respect to some independent variable. Then we can measure what is the rate of change, because if we don't know the rate of change, then it is very much tough for us to identify lots of properties of the system, because entire data will not provide us the actual scenario of the change, but rate of change will provide us that thing. So by differentiation, we can measure that. Another thing is that we can measure the direction along the curve by virtue of the tangent. Why? Because you know that if I consider a circular motion, let's say a particle is rotating in a circular orbit around in that path, through that path. So at any instant, if I want to identify what is the direction of the particle in that orbital motion, then along the tangent, this will be the direction. At this point, along the tangent, this will be the direction. If this rotates in this direction, then at any point along the tangent, we can identify the direction. Similarly, in a curve also, we can identify the direction along the tangent. So we can identify actually unique direction, because at any given point, there cannot have more than one direction. Because say, for example, we are starting from a particular point, we at any particular time, we can go only along a particular direction. So direction should be unique. That's why a derivative of a function, if exist, must be unique. So these are the significances of doing differences. Is that clear, or do you have any doubt? You have already studied this in class 11. So just I'm brushing up this previous knowledge. Is that clear or not? Do you have any doubt? Is it clear? Am I audible?
Yes, sir.
Oh.
Audible.
Is it clear or not? Have you understood this? If you have any doubt, you could ask me. If you have any doubt, without any hesitation, you could ask me. I can repeat this again. Have you all understood? Not. Okay, Aditya, I have understood. So if anyone have any doubt, anyone has any doubt, then you can ask me. Okay. So then we are talking about the function of two real variables, z equals to fxy. So here, if we want to measure the rate of change of the dependent variable with respect to any independent variable, it is not possible, because we can't measure the rate of change of dependent variable with respect to both the independent variables simultaneously. Because as I have told, the dependent variable may depend on more than one independent variable. But whenever we are trying to identify what is the rate of change of the dependent variable, then we can measure with respect to only one independent variable. So here we can consider, instead of the ordinary derivative dy dx, here there are two partial derivatives. One is the rate of change of the dependent variable z with respect to the independent variable x. So here y is kept as constant, and the rate of change of z with respect to y, here x is kept as constant. Okay. So what is the significance of these partial derivatives? Because in the case of function of one variable, you know that we can draw a tangent along a curve. In the case of the function of two variable, there will be three axes. So there will be two axes which are independent axes, x and y, and this is, let's say, z. So there is a surface. So geometrically, z equals to fxy represents a surface. So you know that whenever we are taking a vector in xy plane, let's say, then we can break this vector in two components. One is parallel to x-axis, and other is parallel to y-axis. So the resultant of these two vectors is actually the original vector. So similarly here also, whenever you know the direction cosines means nothing but the concept of the tangent along different axes, different components. That means whenever direction cosine means we are getting the directions of a particular vector along more than one direction, because for the function of one real variable, independent variable is only one. So we can get the rate of change with respect to this independent axis. But here the number of independent axes are two. So here we can actually get the angle of this tangent with respect to x-axis as well as with respect to y-axis. So let's say this is a tangent. So here instead of tangent vector, we'll be getting tangent plane, because this is a three-dimensional axis. So if I draw something, if I take the projection, then the number of variable will be reduced to 2. So instead of tangent axis here, we'll be getting a tangent plane like that. So tangent plane, if I consider the tangent plane, then there is a particular direction of the tangent plane. So this is actually the derivative. So this tangent plane can be actually divided in two parts along these two independent axes, one along y-axis, one along x-axis. So this is called the del z del y. This is called del z del x. So that means here we are getting a tangent plane that is a two-dimensional plane. So there is a particular direction of this tangent plane. So that could be segregated in two parts, two components. One component is along y-axis, another component is along x-axis. So the component of the tangent which we are getting along y-axis is denoted as del z del y, and component of the tangent plane which you are getting along x-axis is denoted as del z del x. So these are the significance for the partial derivative which you have done in first semester. Was it clear, or do you have any doubt? Have you got it? What is the significance? Is it clear or not?
Yes, sir.
Okay. Then what is the significance of differentiability for the complex valued function? You know that in the case of complex valued function, like function of one real variable or function of two real variable, we can't incorporate all those independent and dependent variables simultaneously in one plane. Rather, here we can consider one independent plane, that is the z-argand plane, and one dependent plane, which is the w-argand plane. So here, what we are doing, we are considering fz. Let us consider fz as a function which is a single valued complex function defined in the domain D. Then the definition of this function at z0 is same as the first principle which you did in did for function of one real variable. So what we are doing here, let's say we are considering a point P whose coordinate is actually, or which is denoted by the complex number z0. You know that any complex number can be identified as a two-dimensional point in the argand plane. So in the z-argand plane, the z0, which x component is x0 and y component is y0, is actually identified by the point P. Then we are taking a small increment. So this is the positional vector. You know that this is the positional vector. So positional vector means one point will be connected to origin, and from origin, the vector will be directed towards this point. Now, along this or along any direction, we can consider the increment, small increment with respect to z0. So that is denoted as del z. Now, if I join this end point of this increment, then this will be a positional vector that is denoted as q. So you know that whenever we are considering a positional vectors, so you know the vector law of addition. So with respect to a triangle, we can identify two vectors along any two sides. Then the third side will be the resultant vector. So here also, this one, as per the vector rule of addition, this is the p, that's the increment. So this will be z0 plus del z. So the component are the Poisson vector with respect to q will be z0 plus del z, and the coordinate of q will be denoted by the complex number z0 plus del z. That means x0 plus del x, comma y0 plus del y. So you know that whenever we are defining a function, then each and every value that we are considering in the z-argand plane will be mapped to certain values in the dependent plane. That means w-argand plane. So in the case of w-argand plane, u is the real axis, v is the imaginary axis. So each and every point which we are considering here will be mapped to the dependent plane or w plane. So here, since p and q both are points which are denoted by z0 and z0 plus del z, so they will be mapped to certain points in w-argand plane. Okay. So in the case of w-argand plane, p dash is the image of p. That means z0 will be mapped to f of z0. So that is denoted as w0. Similarly, z0 plus del z will also be mapped. That means the point q will also be mapped to certain point q prime. So the q prime is the image of z0 plus del z. So by virtue of the function fz, we are getting that. That's why the coordinate of q prime will be denoted as f of z0 plus del z. Now, if we join the end point of p and end point of q by a vector, then if the length of this is the difference between these and these, because this is a vector law of addition. So in the case of dependent plane also, so this value of the vector will be f of z0 plus del z. That means w0 plus del w minus w0. So del w, that is denoted as f of z0 plus del z minus f of z0. So what we are doing here, we will be taking here the rate of change of will be measuring the rate of change of dependent variable with respect to the independent variable. So what is the change in a dependent variable that we will be getting from the w plane, that is p prime q prime, and change in the independent variable will be getting by the vector pq in the z plane, that is del z. So f of z0 plus del z minus f of z0 by del z, if this limiting value exists, that means del z tends to 0. That means if p comes closer to q, similarly p dash will also be closer to q prime. So p and q, if p comes closer to q, that means del z will be tends to 0. So limit del z tends to 0, this limiting value if exists, then it will be denoted by f dash z0. Then we'll be saying that the function is differentiable. So function is differentiable means we need to identify first this quotient, that means the change in dependent variable by change in independent variable. Then if the limiting value of this quotient exists, then only we'll be saying that the function is differentiable at the given point z0 and will be denoted as f dash z0. Is that clear or not? Is that clear? Is this clear or not? Just tell me.
Yes, sir.
Okay. Then properties of differentiability. So instead of continuously, it will be differentiability. Just by mistake, I have written over here. So if fz and zz, gz are two functions which are differentiable at the point z0, then sum and subtraction of two functions will also be differentiable at the given point, and this will be denoted as d dz of fz plus minus gz will be derivative of fz at the point and plus minus derivative of gz at the point. Then derivative of product of two functions will be the second function will be fixed, the derivative of first function plus first function will be fixed, the derivative of second function. And if two functions are differentiable at a given point z0, then their quotient will also be differentiable, and the derivative of the quotient will be denoted as this, provided gz not equals to 0. So then we'll be discussing one example where we are given to check the differentiability of the function fz equals to z bar. So like the function of one real variable, here also, if we want to check the differentiability of a given function, we can check by virtue of the first principle. That means here, what is the first principle? F dash z is denoted by limit del z tends to 0, f of z plus del z minus fz by del z. So here we need to check the differentiability of function for any arbitrary point. So no specific point is mentioned over here. So that's why instead of z0, here we will be taking z as any arbitrary point. So if we need to first define this, then if this limiting value exists, so we know how to find out the limit or how to evaluate the limit or how to evaluate the existence of the limit rather by virtue of the path dependent independent method. So similar method we will be adopting here for this quotient. So if this limiting value of this quotient exists, then only we'll be saying that the function will be differentiable. Otherwise, we will be saying that the function is not differentiable. So here del z tends to 0. So del z means here since z equals to x plus iy, so increment in z will be dependent on increment in the real part of the function and increment in the imaginary part of the complex variable. So del z will be del x plus I del y. So this will also be tend to 0. Now f dash z is limit z tends to 0. What is f z plus del z? So z f z is z bar. So z plus del z will be z plus del z bar minus z bar by del z. So since del z tends to 0, so del z means del x plus I del y. So that means limit del x del y tends to 0 0, because real part is del x and imaginary part is del y. And this z plus del z will be x plus iy. Z is x plus iy and del z is x del x plus I del y minus x plus iy bar by this. So x plus iy means x minus iy and del x plus I del y bar means del x minus I del y. Similarly, this will be minus of x minus iy by this. So x iy will be deducted. So this will be limit del x del y tends to 0 0, del x minus I del y by del x plus I del y. Now we need to check whether this limit exists or not. So here, what is the point which is given over here? The point is the origin. So we need to approach towards the origin and we need to evaluate whether the limit exists or not. So we can approach towards the origin through different paths. So either we can approach, so lots of paths are there through which we can approach to the towards the origin. So here we can follow lots of paths, but in order to show that, if we want to show that limit exists, then we can't show by this method, because we need to then show that if we follow infinite number of directions, then the limiting values are coming as same. So by this method of path dependence and independence, only we can show the non-existence of the limit. So towards the point 0 0, we can either approach towards through x-axis and through y-axis. So these are also two arbitrary paths through which we can approach towards the point 0 0. So let us consider that we are approaching towards the through the x-axis towards 0 0. So towards x-axis, if we approach, then the value of y will be 0. So del y will be 0. So del y will be 0 means the limiting value will be dependent on x only. So that means limit del x tends to 0. This will be 0. So del x by del x. So this will be 1. Then similarly, we can approach through the y-axis. So if we approach through the y-axis, then the value of x will be 0. So del x is 0. then the limiting value will be dependent solely on y. So this will be limit del y tends to 0. This is 0, this is 0. So minus I del y by I del y. So this will be minus. So here, while we are following the x-axis, we are getting this limiting value. While we are following the y-axis to approach towards the point 0, 0, we are getting the limiting value as minus 1. So here, the limit of this quotient doesn't exist. So at once we can say that the function is not differentiable at the point, at any point where the function is given as fz equals to z bar. Was it okay? Is it clear?
Yes, sir.
Oh. So then I've shared this study material in the Google Classroom. So I've given some problems over here. So just we will try to solve those problems. And if you can't solve, then in the next class, tomorrow I'll be taking one class. So you can ask me, I'll be solving. So first you try to solve it. And if you can't solve, then I'll be asking. Okay. Then I'll be discussing one more term here. Then I'll be discussing one more term here that is called as the analytic function. So this term is valid only for the function of complex variable. So this analytic concept of analytic function is not valid for function of one real variable or function of two real variable. Rather, this concept of analytic function is valid only for function of complex variable. So why do we need to consider the concept of analytic function, and why it is so important to study for function of complex variable? Because let's say I've given one function, say x equals to mod x, or say function of one variable, just I'm considering, or sin x, or y equals to x square. Then if I ask you to tell me whether this function is differentiable at any arbitrary point, which is a real number, let's say x0 is a point, which is a real number, and I'm asking whether at this arbitrary point x0, this function will be differentiable or not. Then how you can solve it, or how you can answer? Have you got my question? So this function of one real variable is given to you, and I've given the whole real number. That means a set of all real numbers. Then I'm picking off arbitrary point x0, which is a real number. Then I'm asking to tell me whether these functions are as differentiable at any arbitrary real number or not. Then how to answer this question? How will you proceed? Have you understood my question?
Sir, by checking the differentiability at the critical points.
Yeah,
Yes,
at the
sir.
critical point. That means you need to check the differentiability point wise. That means if x0 is the point which is given to you, and you are asked to verify whether this given functions are differentiable at this given point, then by using the first principle, you need to check whether it is differentiable or not. Is that clear? That means you need to check point wise. So without checking the differentiability at critical points or at any arbitrary points at once, you can say whether it is differentiable at any arbitrary points, which is a real number. So this is not possible at all. Is that clear? Because if you are asked to check the differentiability of any function of one real variable, then without checking the differentiability at any arbitrary critical point or any arbitrary point, it is not possible for you to answer whether it is differentiable in all real numbers or not. Is that clear? Is that clear or not?
Yes, sir.
But it is possible for the function of complex variable if we know that the function is analytic function. So what is the analytic function? Consider analytic function. Let's say I'm taking a function of complex variable fz, and I'm saying that it is differentiable at z0. Then it only implies that the function is differentiable at z0. But I can't say whether this function is differentiable at any other points apart from z0, because we know that the function is differentiable at z0 only. So this is point-wise, the function is point-wise differentiable. So I can't say whether this function is differentiable at any other arbitrary point by knowing this information. But we can actually provide this assurance if I know that the function fz is analytic at z0. What does it imply? So fz is analytic at z0 means not only at the point z0, but we can consider any arbitrary neighborhood around the point z0, and the function fz is differentiable at z0 as well as at all other points which are inside that neighborhood. So here, if I consider any arbitrary point z0, so any neighborhood I can construct around that point, I can consider any larger neighborhood. So if a function is analytic, then I know that it is differentiable at all these points. So if a function is analytic at a given point, so it is more broader concept compared to the analytic compared to the differentiability of a function at a given point. Because if the function is differentiable at a point, then only the function is differentiable at this given point. We know that. But if a function is analytic at a given point, then we know that apart from this point, at all other points also the function is differentiable if the points are enclosed within a neighborhood around this given point that we are constructing. Okay, so this is more broader concept. That means if I know that it is analytic at this point, then at all other points which are enclosed within the neighborhood of this given point, then the function is also differentiable at those points. Then there comes the concept. Is that clear? Have you understood this? What do you mean by the analyticity of at a point?
Yes, sir.
Okay. Then more broader concept compared to analyticity at a point is analyticity or analytic function in a domain D. That means if a domain means we are considering an Argand-plane jet, then domain means a two-dimensional region. So if I know that the function is analytic in the domain D, then it is not only analytic at a given point, but it is analytic at all the points in the domain. It is analytic all the points in the domain. It is analytic at this point. Then any neighborhood we can construct around that point, where at each and every point which is there inside the neighborhood, the function is differentiable. Similarly, the function is analytic in that domain D, and this point is also enclosed within that domain. So around this point, I can construct any neighborhood where the function is differentiable. So that means analyticity at a given point means it is only differentiable in a neighborhood around that point. But analytic in a domain means we can consider any arbitrary point from that domain and we can construct a neighborhood around that point. Then the function is differentiable at each and every point in that domain. So this is more broader compared to this. Then after that, there comes the entire function. What is the entire function? So analyticity at a point means we are considering only at one point and we are saying that it is analytic. Analyticity in domain means just we are considering one two-dimensional plane from this Argand plane jet and we are saying that it is analytic at all these points in that domain. Now entire function means in the entire complex plane the function is analytic. That means we can pick any arbitrary point from that Argand plane, not a single point, not a point which is enclosed within a domain, but any arbitrary point we can consider. That means any complex number we can consider, and at this point the function fj will be analytic. So this is more broader compared to the analyticity at a domain. So first there comes analyticity at a point, analytic at a point. Then compared to this analytic in a domain is more broader. Then analytic in the entire complex plane is more broader. Is that clear? Is that clear or not?
Yes, sir.
That means, so the fz is said to be analytic at a given point means fz is differentiable at every point in some neighborhood of z0. Then the function is analytic in a domain D means if fz is defined and differentiable at every point D, that means we can consider any point from that domain. We can construct a neighborhood around that point. The function is differentiable at all these points in that neighborhood. So the analytic in a domain D is considered as holomorphic in D. That means another name of analyticity in a domain is holomorphic in a domain. Then the functions which are analytic in the entire complex plane are said to be entire functions. That means the functions which is not only analytic at a given point, which is not only analytic in a domain, but it is analytic in the entire complex plane are called as the entire function. Okay. So in the next class, I'll be discussing how to check whether a function is analytic. Because if I know that the function is analytic, then without checking the differentiability of that function point wise, we can say whether the function is differentiable in a more large set, a large domain. So in the next class, I'll be discussing what are the theorems through which we can check whether a given function is analytic or not. So let me take your attendance manually first, then I'll be providing you the exam codes. Okay, AIML rule number 1,
Present, sir.
2,
Present, sir.
3, 4. Okay, 4, 5, 6, 7,
Present, sir.
Yes, sir. Sir, 6 also present.
6, 7 given. 8,
Present, sir.
9, 10, 11,
Sir,
Present,
roll
sir.
team present. Sir, roll team present.
10 given.
11.
11,
Present, sir.
12,
Yes, sir.
13,
Present, sir.
14,
Present, sir.
15,
Present, sir.
16, 17,
Present, sir.
18, 19, 20,
Present, sir.
21,
Present, sir.
22, 23,
Present, sir.
24,
Present, sir. 24.
25, 26,
Present, sir.
27,
Present, sir.
28,
Yes, sir.
29, 30,
sir. Present, sir.
given 30,
Present, sir.
31,
Present, sir.
32,
Present, sir.
33,
Present, sir.
34,
Present, sir.
35, 36,
Present, sir.
37,
Present, sir.
38,
Present, sir.
39,
Present, sir.
40,
Present, sir.
41, 42,
Present, sir.
43, 44,
Present, sir.
45,
Present, sir.
46, 47, 48, 49,
Present, sir.
50,
So role 16 AIML present.
So I've given so much time. So just respond why I'm calling your roll number. Right, whenever I'm calling roll number of 1, 2, then others should remain prepared. CSBS roll number 1, 2,
Present, sir.
3,
Yes, sir.
4, 5,
Present,
6,
sir.
6, 7, 8,
Present, sir. 7.
Present.
7, 8 given, 9,
Present, sir.
10,
Present, sir.
11,
Yes, sir.
12,
Present, sir.
13,
Present, sir.
14,
Present, sir.
15,
Present, sir.
16,
Present, sir.
17,
Present, sir.
18, 19, 19, 20,
Present, sir.
21,
Present, sir.
22,
Present, sir.
23, 24,
Present,
25,
Sir, 24 present.
24, 25 given, 26, 27, 28,
27 present.
Sir, 28 present, sir.
7, 8 given, 9,
Present,
20,
sir.
30,
Present, sir.
31,
Present, sir.
32,
Present, sir.
33,
Present, sir.
34,
34 present, sir.
35, 36,
Present, sir. 35 present, sir.
35 given,
34 present.
30, 36,
Present, sir.
Sir,
36.
35%.
35, 36 given, 37, 38,
Present, sir.
38,
38 present, sir.
39,
Yes, sir.
40,
Present, sir.
41,
Present, sir.
42,
Yes, sir.
43,
Present, sir.
44,
Yes, sir.
45, 46,
Present, sir.
47,
Present, sir.
48,
Present, sir.
49,
Present, sir.
50,
Present, sir.
Present, sir.
51,
Present, sir.
52.
Present, sir.
Just wait, I'm sharing the link
Hello,
for today.
sir.
Yes,
Sir, AIML roll 50 present, sir.
15.
50, sir.
Sir,
50.
CSBS roll 23 also present.
Sir,
So-
AIML 35 also present.
Okay. So I've shared the link as well as the exam codes. So just click the link and provide your full enrollment number and exam codes and give the test. So someone from CSBS and AIML, just check and let me know whether you can access it right now.
Sir, roll number 23 CSBS present. Please check.
Given though, you have told once, so why are you repeating?
Sir, for CSBS, it's working.
Sorry? CSBS?
For CSBS, it's working, the codes.
CSBS, what is roll number?
Sir, I said that the codes are working for CSBS.
Okay, thank you.
Sir, for AIML also it's working.
Okay, thank you, V.
Sir, AIML roll number 9, I could not unmute when you were taking attendance.
Okay. Okay, so thank you all for attending today's class. So just
Sir, roll number 37 CSBS. Can you sir mark? Can you please check that whether you have marked me present or not?
have you responded?
Yes, I have. Actually, sir, my headphone was not working. So I had to-
37.
Yes, sir.
Yeah, you have given.
Okay, sir.
Okay, thank you all. I'm leaving. So tomorrow I'll take the class on 4th period. Okay, thank you.